Our lesson for today is integration or anti-differentiation. But before we start our lesson, let us recall some of the differentiation formulas. So these two tables show us derivative of some functions. The first column are functions. The second column are their derivatives. Let us look at the first table. The first formula is the power rule for differentiation. The second formula is the derivative of logarithmic function. Take note that ln of a is constant. When the base is e, the logarithm is simply written as ln of x, and its derivative is 1 over x. Next is the derivative of an exponential function. When a is e, its derivative is itself. These are the derivative of the 6 trigo functions. These are the derivative of the inverse trigo functions. Take note that the derivative of arc cosine, arc cotangent, and arc cosecant respectively are the negative of the derivative of arc sine, arc tan, and arc secant. The remaining formulas are some of the fundamental formulas for differentiation. This is the constant multiple rule for differentiation. It is telling us that numerical coefficients are simply copied. This is the sum rule for differentiation. When you differentiate a sum, you simply differentiate its term. This is the quotient rule for differentiation. Low derivative high minus high derivative low over the square of the denominator. This is the product rule for differentiation. So left derivative right plus right derivative left. And this is the general power rule for differentiation. So what is integration or anti-differentiation? In Calculus 1, given a function f, we are asked to find its derivative. So the operation that is performed is either prime or d over dx. If the resulting function is g of x, then it is denoted by f prime of x or d over dx of f of x. And such function is called the derivative of f of x. In Calculus 2, in this course, we will do the reverse. Meaning to say, given g of x, we find not only f of x, but the set of all functions whose derivative is g of x. When a constant is added to f of x, its derivative is still g of x because the derivative of a constant is 0. So when an arbitrary constant is added to f of x, then this represents the set of all functions whose derivative is g of x. And this process is what we call integration. So integration is the process of finding the set of all functions whose derivative is a given function. The operation that is used is this one. So when this is performed on g of x, it is written in this way, and this is read as integral of g of x with respect to x. And its value, as I was saying a while ago, it is the set of all functions whose derivative is g of x. So c is an arbitrary constant. So these are the things that we need to remember. The integral of small f with respect to x is capital F of x plus c, where c is an arbitrary constant, provided that the derivative of capital F is small f. Capital F is called an antiderivative of small f. So this rule in evaluating an integral is telling us that it is enough to find one antiderivative of small f if such antiderivative has a constant term. When it is added to c, the resulting is again an arbitrary constant, so it can be simply written as a c. So what I'm saying is that our answer is unique up to the arbitrary constant. Small f is called the integrand, and c is said to be the constant of integration. So to illustrate the idea, let us look at some examples. The derivative of sine x with respect to x is cosine of x, and therefore the integral of cosine of x would be sine of x. So we have this one. The integral of cosine of x with respect to x is sine of x plus an arbitrary constant c. The derivative of x cubed with respect to x is 3x squared, and therefore the integral of 3x squared with respect to x, it would be x cubed. So we have this one. The derivative of 2 to the x over ln of 2, when we apply the constant multiple rule for differentiation and the derivative of an exponential function. So you copy 1 over ln of 2. When you differentiate 2 to the x, it would be 2 to the x times ln of 2. So it will cancel with ln of 2. So the resulting, it would be 2 raised to x. And therefore, the integral of 2 raised to x would be 2 raised to x over ln of 2. The derivative of arctan of x with respect to x is 1 over 1 plus x squared, and therefore the integral of 1 over 1 plus x squared, it would be arctan of x plus an arbitrary constant c. So this would be the first set of integration formulas. The first one is the constant multiple rule for integration. So it is saying that numerical coefficients are simply copied when you anti-differentiate a particular function. So for instance, the integral of 5 sine x with respect to x, you copy 5 and then you anti-differentiate sine x with respect to x. This is the sum rule for integration. So when you integrate a sum, then you integrate each term with respect to x. So for instance, if we want to differentiate this polynomial function, then it would be equal to the integral of the first term minus the integral of 8x cubed plus the integral of 9 with respect to x. This is the power rule for integration. When the exponent is not negative 1, then the value of the integral, it would be x raised to n plus 1 over n plus 1 plus an arbitrary constant c. However, when the exponent is negative 1, then the value of the integral would be ln of the absolute value of x. If you look at the table of differentiation formulas, the derivative of ln of x is 1 over x. However, in the domain of the function, x should be positive. But when we integrate 1 over x, x can be positive or a negative number. So the integral of 1 over x would be ln, not only x, but absolute value of x. So that ln is defined when x is negative. So remember, when n is negative 1, that is when we have 1 over x, so the integral of 1 over x with respect to x, or the integral of dx over x, it would be ln absolute value of x plus c. Just to illustrate the power formula, the integral of a constant with respect to x is simply k times x plus c, because the integrand can be written as k times x to the 0. When we want to differentiate this sum, so the integral of the first term, you copy 5, the integral of x to the 4, that would be x to the 5 over 5, minus, you copy 8, integral of x cubed, that would be x to the 4 over 4, plus integral of 9 with respect to x, that would be 9x. So you have this one. So when you simplify this, it would be x to the 5 minus x to the 4 plus 9x plus c. The integral of cube root of x, you write the radical as a rational exponent. So power rule for integration, the integral of x to the 1/3, it would be x raised to 1/3 plus 1. That would be x raised to 4 over 3 over 4 over 3. When you simplify that, it would be 3 over 4 times x raised to 4 over 3. The integral of 1 over x squared, you write this as a negative exponent. So you have x raised to negative 2. So applying the formula, the integral would be x raised to negative 1 over negative 1, or negative x raised to negative 1. When we simplify this, it would be negative 1 over x plus c. Formulas 4 to 9 are, this is the first set of integration formulas involving trigo. And these formulas can be, again, derived from the table of differentiation formulas. So looking at this part, the integral of cosine of x would be sine x. The integral of sine x, the negative sign will go to the left. So the integral of sine x would be negative cosine of x. The integral of secant square, it would be tangent of x. The integral of cosecant square, the negative sign will go to the left. So it would be negative cotangent of x. The integral of secant of x, tangent of x, it would be secant of x. The negative sign will go to the left. So the integral of cosecant of x, cotangent of x, it would be negative cosecant of x. So that would be formulas 4 to 9. The formula in 10 is this is the integral of an exponential function. So again, ln of a is constant. So in particular, when a is e, the integral of e to the x would be itself, because ln of e is 1. Just to illustrate the formula, the integral of 5 to the x with respect to x, it would be itself over ln of 5, which is the base. The remaining formulas are integrals yielding inverse trigo. We don't have, I did not include our cotangent, our cosine, and our cosecant, because these formulas can be obtained from these three formulas, because the derivative of our cotangent, our cosine, and our cosecant are the negative of the derivative of arc tan, arc sine, and arc secant respectively.